Hello all, thank you for joining this session. We'll just give it a minute while everybody switches from the previous session to this session, and then I will go ahead and introduce the speaker. Thank you. All right. Hello, everyone, again. Thank you for joining the session. So I'm going to introduce the speaker here, and today I have the privilege of having Max Lippin from H3X Technologies. Just to introduce the speaker, Max Lippin received his bachelor's degree in mechanical engineering and pursued his master's in electrical engineering from University of Wisconsin at Madison. During his undergraduate studies, he co-founded the engineering student organization, Wisconsin Racing Formula SAE Electric, and went on to design high power density in-hub motors for their electric race cars. During his graduate studies, he was a research assistant to Professor Daniel C. Ludos at Wisconsin Electric Machines and Power Electronic Consortium, WEMPEC, with a research focus on permanent magnet ring machines with integrated propellers. After graduation, he worked at Tesla as a powertrain performance modeling engineer before co-founding H3X Technologies, where he is currently developing high-performance integrated motor drives for flight applications. Today, we have the privilege of listening to Max as he's going to talk about design of an integrated motor drive with a highly saturated, high-frequency electric machine using JMAG. With this, I would like to welcome Max onto the screen and talk about his presentation. Thank you.
Great. Thanks, Fed. Thanks for the introduction and also for inviting me to speak today. My name is Max, and today I'll be talking about an integrated motor drive. I'm here representing my company, H3X Technologies. There are three of us that founded H3X. I'm the CTO. Ved already kind of went over my background, so I won't repeat that, but I have worked at Tesla and SpaceX, and a bunch of my co-founders have also been at either WEMPEC or one of those companies as well. So in terms of the business, just to kind of overview what we're working on, we're making this integrated motor drive and variants thereof for a couple different markets. Most are flight applications. So today, a lot of unmanned aerial vehicles like cargo UAV, and into the future, urban air mobility, flights less than 50 miles, you see air taxis, in development right now. Also regional air mobility. There was a NASA study that came out that I highly recommend on regional air mobility that talks about utilizing the 5,000 airports in the United States that of which 500 are only fully utilized right now. And then eventually large commercial electric aircraft. But it'll take a bit of time to get there. So in the meantime, we're also having a lot of success, getting pilot customers in the electric marine space and also high performance ground vehicles. So now is the time to start working on this problem. Right now, aviation only accounts for 2% of greenhouse gas emissions worldwide, but that's growing rapidly as more people get access to flight, and also as other areas like automotive will begin to decarbonize in the next couple of years. So now's the time to start working on the problem. But right now, the electric propulsion systems are way too heavy for flight applications. A DOE study showed that you need 12 kilowatts per kilogram with 93% cruise efficiency for a narrow body jet like a 737 to complete a 5-hour flight. But the current systems are only 4 kilowatts per kilogram. So we have a 3x improvement in specific power is needed to get there. So today I'm going to talk about kind of how we are working on that 3x specific power improvement, which also is part of the company name H3X. Just to walk through what we're going to talk about, I'm going to start with really basic stuff, definitions. I'm going to propose a kind of a unique framework for thinking about the problem in terms of specific force and tip speed, which is a little different. And then I'll talk about some common figures of merit that we like to talk about that maybe aren't the best. And then we'll go on kind of bringing this into how does JMAG help us with this optimization, defining those optimization goals within the framework. We'll talk about that air gap force and tip speed, how it relates to material properties, manufacturing processes, and then we'll look at some JMAG results that are particularly interesting and go over an overview of our technology demonstrator. So for flight applications in particular, mass is the highest sensitivity. There's also volume sensitivity for the propulsion system, but mass is a much greater sensitivity. So, specific power is kilowatts per kilogram, whereas power density kilowatts per liter. We care about specific power. So you can have two motors with the same outer diameter and power rating, but obviously the one on the right will be much lighter, even though they occupy the same volume. So we're focusing on reducing mass. Traditionally, we like to talk about specific power in kilowatts per kilogram as the product of specific torque, newton meters per kilogram, times rotational speed. And in this sense, you have kind of a fixed machine design. If you can make the rotor spin faster, then you get a higher specific power, more RPM, more better. Torque is proportional to mass. But I argue that this is only true for a fixed air gap diameter, and that when you fully open the design space, I think the framework on the right is actually a lot better way to think about it. So kilowatts per kilogram can also be represented as a specific force in terms of the air gap force divided by the machine mass multiplied by the rotor tip speed. So in this case, more meters per second is more better instead of more RPM. And also that air gap force is proportional to the machine mass, not the torque. So I'll kind of walk through and show how the specific force and tip speed are directly connected to material limits, whereas rotational speed and specific torque actually aren't tied to inherent material limits and are therefore kind of poor figures of merit when you're really trying to increase specific power or reduce mass. So these are the figures of merit I kind of want to talk about that I think are tossed around a lot, but maybe not the best. Rotational speed, specific torque, and current density. So I'm going to show how all three can be increased without really improving any of the materials or manufacturing processes. So with sort of a trivial geometry change, you can increase any of these. First one's rotational speed, and I'll use radial and tangential stress in the rotor sleeve as an example. There's a lot of math, but the takeaway is that the radial and tangential stress in the sleeve is proportional to the rotor density times the rotational speed squared times the outer radius squared. And so that rotational speed squared times outer radius squared is really just the rotor tip speed squared. So if you solve for the rotor tip speed, you get that it's proportional to the square root of the maximum allowable stress in the sleeve material divided by the rotor density. So you can see tip speed's directly tied to those mechanical material properties of the rotor. So if you have a 30,000 RPM machine that's this big, or a 10,000 RPM machine that's this big, the 30,000 RPM machine is not necessarily more impressive. It's the same tip speed, so it's operating at the same material limits, but obviously they're different RPMs. Next, I want to talk about specific torque. I think this is particularly ubiquitous in terms of people comparing one machine to the next in terms of newton meters per kilogram. And so I'll take one machine, like the small one on the left, and we're going to scale it to a larger machine, but keeping the rotor thickness and the stator thickness the same. So the way that you can think of that is we're going to unroll the small machine, and then we're going to multiply it in length or number of poles by a factor K, and then we're going to roll it back up. So the same per pole design is used. It's just patterned over K number of times. So we can just kind of walk from basics and walk through this real quick. Force is ILB, and if you rewrite that, you get it that it's current density in the conductors, amps per millimeter squared, that's your J. Your conductor area times your length into the page, and then your fundamental air gap flux density magnitude. So you can see the original motor here, and then the scaled version here. The conductor area is whatever it starts as, and then the next conductor area after scaling is linear with the scaling factor K. So because the conductor area is the only thing that changes in this equation, since the current density, the length into the page, and the flux density are the same for every pole, we get that force scales with K because conductor area scales with K. And then, just by looking at it, you can tell that the mass scales also with K. So with the scaling factor K, we get that this specific force is constant. The force per mass is independent of how long I make this linear machine. But what's interesting is when you roll it back up, you get that the scaled torque actually goes with K squared. And that's because the force is linear with K, but the radius is also linear with K. So you get torque with K squared, but your mass is still only with K. So your specific torque in newton meters per kilogram scales with K, which if you just kind of boil it down, just means that if you have a certain per pole design and you want higher specific torque, just put a lot of poles all the way up at the periphery as far as you can. So it's sort of a trivial thing. So that's why if you have a small machine that's 20 newton meters per kilogram, or a larger diameter machine that's 60 newton meters per kilogram, they're operating at the same specific force, and they're both operating the material limit. So it's not like the 60 newton meters per kilogram is inherently more impressive in any way. It's just a different geometry choice. I go through a whole lot of detail in the scaling in my paper, which I kind of have on the bottom left of the slide here if you want to go through the weeds and take a look. Last one is current density. I'll try to go through this quickly. I don't have time to walk through all the equations, but we hear a lot that 40 amps per millimeter squared is a lot more impressive than 20, but that's not necessarily the case. So if you have a winding bundle, like the one on the left, at some thickness, and we're just going to use a 1D plane wall as simple as possible to sort of characterize this, that is XB thick, and then again, we just scale it by a factor K. I want to see how the allowable current density changes. So if you go through all the heat transfer analysis, you get that your delta T, which is a function of, on the high end, your maximum allowable insulation system temperature, and then on the boundary temperature condition is your coolant. So that delta T has to always be the same if you're operating at the winding temperature limit at the hotspot, and that's proportional to the product of your current density and your bundle thickness squared. So even after scaling, I still have to have the same delta T. So what happens is that as I scale it, the current density has to go down. And this is sort of intuitive in the sense that if you have a bigger bundle, there's going to be a higher temperature drop from the inside of the bundle to the outside if you're running at the same current density. So in order to maintain that temperature drop, you have to reduce the current density. Takeaway is very high winding current densities are achievable for very small coils. Another way to look at this is if I have, say the big and the small machines are both 4-pole machines. The per pole geometry on the larger machine is much larger. And so I have much larger bundles of copper or whatever your conductor is. And so I could operate the small one at 45 amps per millimeter squared and the large one only at 15, but they're both at the same winding temperature. They're both operating at the material limits of the insulation system, but they're different current densities. So it's not really an apples to apples comparison. This just kind of repeats everything I just went through. None of these are really good figures of merit because you can sort of manipulate them in ways that are somewhat trivial. So how do we do better? How do we reframe this problem? So kind of going back to the original idea, describing specific power in terms of specific force and tip speed, There's, again, a lot of equations here, but it's just rewriting the air gap force, ILB, in terms of your current density and your conductor area, J and A. Your active mass is proportional to your active volume, which is, of course, your active area times your length. So you both have length into the page on both sides here, so that kind of drops out. And you get that your specific force is proportional to current density, your conductor area, your air gap flux density, all divided by your active cross-sectional area of your machine. And then of course you have rotor tip speed, which we already went over. So if you take the product of those, you get this ratio. Like I said before, the current density in each pole of the machine, the flux density in the air gap, and the tip speed at the rotor are the same for every pole in your machine. So you can reframe the conductor area in the numerator and the active area in the denominator as the per pole conductor and active area. So then you can think of the specific power as a per pole specific power. This makes sense intuitively. When we model things in JMAG, we typically are modeling the minimum number of symmetries, and depending on the machine, a lot of times that is just a single pole. So this is how we think about at H3X, what we're using JMAG for, is we're using it to find that optimal per pole geometry that in our case maximizes specific power, subject to some other constraints as well, of course, given the material properties and manufacturing technologies that impose limits. So assuming you have sufficient computational power and you can do a lot of modeling and evaluate a lot of geometries, there should be an optimal pole geometry to achieve your goals. But when you take that out of the equation, assuming that you can find that geometry, that specific force and tip speed are both inherently tied to material limits and manufacturing technologies. And they're both individually a limit of those things, and the product then, of course, is also a limit of those things. So a lot of times, over the last couple of years, I've heard over and over and over again that torque is proportional to mass. That's how you should think about it. But if you're really allowing the design space to be as open as possible and you're operating at material limits and you're able to find that optimized per pole geometry, then specific power is actually a constant limit, and therefore power is proportional to mass, which is a little strange. At least it was definitely strange to me the first time I went through all this. So then the question becomes, how can we improve the materials and the manufacturing processes to push the limits of the specific power when we have a tool like JMAG that helps us, develop the optimal geometry? Again, a lot of equations on here. Feel free to read through if you want in the recording. But what we're looking at here is really like rewriting the specific force and the tip speed in terms of its component material properties. And so we'll just focus on this equation here, which is the result. And I'm going to talk about briefly all these different factors and how they influence the output power. Anything in orange is something that we're working on at H3X in a significant way. And then anything in black is something that is either state-of-the-art that we're using, or it's just not something we're currently working on. So your output power is proportional to your conductor fill factor. We all know this. And we're working on additively manufactured coils made out of pure copper to increase the conductor fill factor. We're also working on a different coil design that uses stranded wire, but that is incredibly compacted and still maintains the required insulation characteristics. Next over, you have your air gap flux density, which of course is a function of your material properties and your magnets, your steel, but it's also a function of your stacking fixture design and the materials that you use, like your rotor or your stack adhesive. Also, rotor cooling can impact this through the magnet flux. And we're working on flux concentrating rotor topologies as well as Halbach configurations. The conductor resistivity, which is a function of temperature, is also very important. One way to keep that resistivity as low as possible is having in-slot cooling. That's something we're also developing at H3X. Otherwise, these come from tip speed. You have rotor density, maximum rotor stress. These all go into your rotor design. Moving on, your maximum delta T, like I described before, function of both your insulation temperature limit. So that's one thing we're working on is a very high temperature insulation system capable of operating continuously at over 260 degrees C for a lifetime of that 20,000 hours. And then of course you can also make your coolant colder. And last is the thermal conductivity. And this is the effective thermal conductivity from the hotspot in the bundle all the way to the coolant. And so there are a lot of different materials in that chain, but one of the biggest ones, of course, is your high voltage insulation system. And that consists of your conductor insulation, your transreturn insulation, and your coil to ground slot liner, typically. So we're working on a very high thermal conductivity insulation system with some novel materials that also allows us to have a higher conductor fill factor. And the more copper you can pack in there, actually the higher your thermal conductivity is effectively through the bundle. So everything kind of affects itself. And lastly, minimizing contact resistances. So that's all, maximizing output power for a given set of materials and for a certain mass. There's also inactive mass reduction, which in an integrated motor drive matters a lot. So normally when you have a motor, an inverter, and a gearbox, you have a bunch of housings, a bunch of cooling systems. So we're integrating all of those housings into one part. So we have a gearbox, a motor, and an inverter all attached to one housing. And that same part, that same housing also integrates the cooling system that synergistically cools all three of those things. So we can get rid of a lot of additional inactive mass. And lastly, this isn't related to the machine design or JMAG, but it's important to talk about, is the power electronics mass reduction. So we're working on silicon carbide inverters and using silicon carbide power modules with high switching frequency. And what comes with the territory is very low inductance, tightly integrated DC link design, which is super important to really maximize the utilization of those silicon carbide switches. And lastly, using some kind of novel EMI and EMC reduction techniques so that we don't need to have a heavy common mode filter. Just to jump into the JMAG part, kind of actually get some cool plots up. When I'm talking about optimizing the per pole geometry or the minimum number of symmetries that you simulate in JMAG, here's an example of what that looks like as a Pareto frontier. It's a little sparse because I cleaned it up just so you can kind of see better what's going on. But this is just plotting the slot depth of the stator and how it affects the specific power and motor efficiency. So this is running each solution at the maximum current density, which is based on a thermal model for that particular geometry. And you can see that specific power really plateaus at some point. You're not really getting much more specific power out as you increase the slot depth. But your efficiency is starting to go down significantly. So there's a good trade-off point. And lastly, your power factor also changes as you increase your slot depth. And typically, if you want your short circuit current to be right around your rated current, which means you have a thermally sustainable three-phase short condition, then your power factor at rated current is going to be around 0.7. And that actually works out well here because that's a good trade-off point between efficiency and specific power. So we've discussed, we're working on innovative materials, manufacturing processes. We use JMAG Designer to find the optimal pole geometry, but let's talk about how else JMAG has helped us save a lot of time and money in our prototype production process. So in order to hit these really high specific powers on a system level of over 12 kilowatts per kilogram, so on a motor active mass level, 25 to 30 kilowatts per kilogram, the magnetic circuit has to be extremely saturated. There's no way to avoid it. And when you do that, of course, you have fringing flux that goes everywhere, through the slot, through the shaft, through the housing. There's flux flying everywhere. And so that presents challenges. And JMAG helped us find kind of the egregious eddy currents that are generated in all the conductive components early on in the design process. So right in our first preliminary design evaluation, we're able to quickly identify these issues before we actually go and build our hardware. So those three instances I want to focus on are our simple geometry of our additively manufactured coils, the shaft design, and the housing design. So you can see we have some wide flat turns in the slot of our additively manufactured coil. That's what these lines are. You can see there's some fringing flux. This is just open circuit, no stator current flowing except for eddy currents. And even open circuit, no load, you still get over 100 amps per millimeter squared in your conductors near the air gap. So super high eddy currents. And when you actually go under load, as I said, highly saturated, high frequency machine, you get 1.6 Tesla fringing into the side of the teeth. And it's completely prohibitive. Like the design does not work at all. So you can't make a coil for a machine like this, but you can make these coils. They're just not useful for a machine like this. And we learned that very quickly in the beginning. So obviously this entire area is completely out of the ballpark of where it needs to be. And so open circuit and under load, we go from 10 kilowatts of just eddy current losses to 30 kilowatts. It doesn't make any sense. It doesn't work. It's a 250 kilowatt machine. The conductors would fuse themselves. So obviously it was important to improve the design. Next, shaft eddy currents. We had 150 watts at no load, but under load, you can see the blue line here goes all the way down there, and we ended up with 5 kilowatts. Can't have 5 kilowatts of heat in your rotor. Based on the thermal resistance to the coolant, the allowable losses are about a couple hundred watts total, so didn't work at all. Again, had to redo the shaft geometry in order to rectify this problem. Lastly, housing eddy currents. Here's your back iron, and this section is the housing. You got one flux line that's leaking out of the back iron. Doesn't look so bad just when you look at it like this, but you can see the eddy currents are red and purple, very high eddy currents right in this area. Overall, the losses aren't too bad. It's about 1 kilowatt, and this is at a takeoff condition. So this is at like 200 kilowatts or 250 kilowatts. So 1 kilowatts of loss is tolerable. The losses are much lower at cruise, which would be at cruise condition. It's about 2/3 rated speed, 1/2 rated torque. So this is acceptable, but still, a significant loss source. So thanks to JMAG, we were able to identify and fix all these issues pretty early on in the process. We revised our AIM coil design with a more complex geometry to reduce those AC losses. We changed the shaft and housing design slightly in order to eliminate those egregious losses as well. And you can kind of see in this little rotating picture here what our integrated motor drive kind of comes together as. And so I'll give a kind of high level overview of the integrated motor drive that we're working on. So our first product, the HPDM 250, it's integrated with a gearbox, motor, and inverter, and multiple areas of innovation. Some key ones are, of course, electromagnetic optimization with JMAG, novel thermally conductive, partial discharge resistant, high voltage insulation system, silicon carbide power electronics, and a very high performance DC link to support it. Additively manufactured housing / thermal management system for synergistic cooling, and what we think is the highest level of integration on the market, which is to say, we're not taking a motor, which is a cylinder, an inverter, which is a box, and just slapping the box on top and calling it integrated, which you see a lot. Our power electronics, DC link are really tightly wrapped around the machine. And so what you end up with is a product that takes everything from the DC cables all the way out to the output shaft to be connected to your load. So it's very plug and play, and that represents cost savings for the customer, even if the unit itself is a little pricier than a normal motor. Here are some specs. We're currently in the midst of building our prototype. We've almost finished the rotor. All of our stator parts are ready to go, and we're doing a bunch of partial discharge testing of our thermally conductive insulation system on our coils, and we hope to have our first prototype fully assembled and starting loaded testing within the next 6 weeks or so. Thanks for coming. Hopefully I didn't go over. It's about 1 slide per minute. Please send me an email at max@h3x.tech if you have any questions, or submit questions through the Q&A. Otherwise, check out our website, h3x.tech. And thanks again for having me, Ved.
All right, perfect, Max. Thank you very much for this wonderful presentation. It's quite insightful, and congratulations on coming up with ultra high fidelity power density integrated motors. Some of the work that you have been doing from last couple of slides we have seen. Congratulations on that, and thank you very much for presenting how JMAG was helpful in this entire design process. So everyone, the floor is open for questions. If you have any questions, you can always post it on the Q&A panel while we have Max here for the next 5 minutes or so to answer any of your questions. All right, let's go ahead and see. So one of the incoming questions I see, Max, here is in one of your slides, you said 100 amp per millimeter square is quite high. What kind of cooling did you use?
Yeah, so that design we didn't use. We can't use it. It's way too high of a current density, except maybe if you have coolant touching the conductors directly. And so we revised the coil design instead to reduce the AC losses in the conductors from the fringing rotor field that proximity effect. We fixed it in the design instead of fixing it with cooling, because that was kind of the better way, both from the thermal standpoint, but also from the efficiency standpoint.
Okay, perfect. Let me see. So what's the new current density then? Just continuing with the same question.
Yes, so I caution you with using current density to compare apples to apples. But yeah, our maximum continuous current density right now is on the order of 40 amps per millimeter squared. But again, it's a relatively small bundle. It has very low thermal resistance. Yeah.
Right. And in last couple of slides, you have shown two different motors. Are both of them tested, or is one of them in the prototype phase? Can you throw some light on this testing?
Yeah, so
simulation?
Yeah, I'm not sure which two you think the pictures are, but they're all the same. So this is just with the outer cover off on this slide, so you can kind of see the DC link and the power electronics wrapped around. This one has the integrated gearbox on the front. So that's what that kind of little extra length is on the front there. It's a planetary gear reduction. And then just the same view here. This was actually without the gearbox on the front. So this is the direct drive version. So maybe that clarifies things a bit.
And one other question, of course, nice presentation. I'm curious about these power density specific power numbers. Are these specific power numbers based on the total mass of the rotor or just an active material?
Right. So the specific power of the active mass of the machine is based on not the rotor shaft. So that I didn't include the rotor shaft in the active mass specific power for the motor itself. But I should clarify, I don't know if I was clear about this or clear enough about this. The integrated motor drive as a whole with the gearbox is roughly 12 kilowatts per kilogram, and that's continuous, and that includes all of the active mass and the inactive mass altogether, everything with gearbox, housing, and all that stuff. So that's that 12 kilowatts per kilogram target. That is a continuous number with everything included in it.
Perfect. Hope that answers your question. But if you do have any other questions, you can always contact Max on the HUA app, and he will be able to directly answer to you. Or you can also, as Max said, you can also contact him via his email, max@h3x.tech. But we'll just wait for a couple of seconds if there is any other question coming in. Let me just quickly look here.
I definitely threw a lot out there. So, you know, there will be a recording available if you want to take a longer look at any of the slides.
Yep, absolutely. The recording will be available on the HUA app for about a week or so, and then it will be also on our website. In case you are interested, you can go there and look at it, and always write to us if you have any questions. But I think those are the questions for now. But if there are any other incoming questions, Max, you can always answer them on the HUA platform directly in the chat box. Oh, I think there is one incoming. If you don't mind, if you can take that as well.
No, yeah, by all means.
Okay. How did you optimize the machine with multiple operating points?
It's a good question. So I don't have a picture of it, but there is sort of a duty cycle versus time versus power for like a typical narrow body jet 5-hour flight. So for our first technology demonstrator, we used that 5-hour flight profile as the design target. And that consists of mostly a cruise, which is at 1/3 of takeoff power. And so that's like over 90% of the time is spent there. And then there's also, you know, takeoff, which is on the order of 10 to 15 minutes, which is still thermally continuous for a lot of the components in the machine. So that takeoff condition kind of limited, you know, where we need to be performing for maximum continuous thermal capability. And then the cruise condition is really what drives where we want the heart of efficiency to be.
All right, perfect. So thank you very much, Max, for this wonderful presentation. I know it was quite insightful with all the theory. Also, you have very well defined. But as I said, if there is any other questions, we can always answer in the HUA app, and or you can always contact Max, guys. Just continuing with the last question on the optimization, it's quite interesting because the next session is about optimization in JMAG. I would request everybody to switch over to the next session in a couple of minutes so that you can hear about motor design using topology optimization and parametric optimization by our senior support engineer, Dheeraj Boga. And as you move to the next session, please refresh your page in case you have any technical difficulties. And once again, Max, thank you very much for accepting to speak at our conference and for your contribution. Thank you. And
yeah, thanks for having me.